is your instructor of the subject Foundation Engineering, and today we are going to discuss the ultimate bearing capacity of this shallow foundation. Okay, so before we will proceed, I will just give you some overview or a sort of introduction of this topic, considering this shallow foundation. Okay. So we are going to start with this definition of the ultimate bearing capacity, in which this is the load per unit area of the foundation at which shear failure in soil occurs. Okay, so we have now this figure 1, considering this general shear failure as part of our general concept. Okay, so as you can see it here, we are going to consider strip foundation with the width B, the width of this foundation resting on the surface on a dense sand or this stiff clay, and this is cohesive soil. Now, if a load is gradually applied here to the foundation, settlement will probably increase. Okay, and the variation of the load per unit area on the foundation, which is denoted by our variable, considering this load per unit area with this small q. Okay, with the foundation settlement is also shown in this figure. Okay, at a certain point when the load per unit area equals now this q ultimate, this is denoted by this q sub o, a sudden failure in the soil, okay, supporting the foundation will take place. Okay, so take note of that. And the failure surface in the soil, in this case this one, we will consider this one as the failure surface in soil, and the failure surface in the soil will extend to the ground. From here, this will extend now to the ground. Actually, this is now our ground level, represented by this dash line, and this load per unit area, when it reaches q sub o, or the ultimate value, is usually referred to as the ultimate bearing capacity, okay, of the said foundation. And when such sudden failure in soil takes place, and we call this one as the general shear failure. Okay, so by this illustration on the right side of this figure, we can see that there is the load per unit area in the x-axis, and we have also now the settlement in the vertical axis. As you can see, if the load per unit area increases going to the right, so this settlement line, represented by this color blue, will have now this settlement with respect now to this load per unit area, until such that the value of your load per unit area reaches to a maximum or ultimate, denoted by this QU. So this would be now its corresponding settlement, and you can get now its value as you extend this one with a line from this point to this vertical axis, and you can get now your settlement. Okay, so remember that when at a certain point, when the load per unit area, applied it here, okay, when the load per unit area equals now to this q sub u, a sudden failure in the soil will occur. A sudden failure, this is the thing that you have to remember. A sudden failure will occur, and by this we shall consider this one as a general shear failure. Okay, so when sudden failure in the soil takes place, it is called a general shear failure. Okay, so proceeding now with our next slide. Okay, we have now this local shear failure, and from this figure, as you can see, if the foundation under consideration rests no, on this type of soil, which is sand or clay soil, we can say that when it is a sand or clay soil, it is considered also as a medium compaction, no? Meaning an increase in the load on the foundation will also be accompanied also, no? The same as for the general shear failure, it is accompanied also by an increase in settlement as we increase the load. But however, in this case, the failure surface in the soil here, this is the failure surface in the soil now if we are going to consider the right side, and it is just symmetrical to the left side. Okay, the failure surface in the soil here will gradually extend upward. Okay, this is will gradually extend upward, no? From this point it will gradually extend upward. Okay, outward to the soil, no, to this ground surface, and it is represented, no, by this broken line or dashed line. Okay, it will extend outward, no, to the soil surface, and in the load per unit area on the foundation, if you are going to consider uh, this one part, no, of your Q sub U. Okay, when the load per unit area of the foundation equal now to this Q sub U1, the movement of the foundation will be accompanied, no, by a sudden bump, no, a sudden bump, meaning there will be a jerks, no, or bouncing of the soil, and because of this, a considerable movement of the foundation is then required, no, for the failure surface, no, in the soil here to extend to the ground surface as it is represented by this dashed line. Okay, so the load per unit area at which this happens is the ultimate bearing capacity. Okay, and we denote this one as this Q sub U. Okay, remember this one, the load per unit area at which when this one happens, no, that there is a considerable, no, jerks, bouncing back or bumping, no, when your load per unit area of the foundation equal now to this Q sub U1. So it is called now the ultimate bearing capacity. Okay, so beyond that one is there will be an increase, no, in load. The increase in load will be accompanied, no, by a very large increase already, no, beyond this point, no. Beyond this point, there will be a considerable increase in foundation settlement, and the load per unit area, no, of the foundation, this Q1, is referred to as first failure load, no, according to BSIC of 1963. And as you can see, no, that a peak value of Q is not realized in this type of failure, which is called the local shear failure. Okay, so this is now the graph, no, of your load per unit area Q with respect now to the settlement, in this case now considering the local shear failure. Okay, so you have to remember for this local shear failure, the type of soil that you have here is probably you have a sand or clay soil, no, which is we consider this one as medium compaction soil, no. And when you are dealt with this type of soil, it is called a local shear failure, no, and you may consider this one in your design, no, considering local shear failure. But in terms of the general shear failure, as you can still remember, no, from our first slide here, you are dealing with this dense sand or stiff clay, no. So when you encounter this one, so you have to consider the general shear failure. Okay. So proceeding now with our next slide, we have this punching shear failure. Okay. So as you can see, if the foundation is supported, no, by this fairly loose soil, so as you can see in the figure, the load settlement plot, no, will be like this, no, for this punching shear failure. So in this case, the failure surface, no, as denoted by this one, okay, in this soil will not extend, no, will no longer and will not extend now to the ground, no, to the ground surface. It is only up to here, okay. And beyond the ultimate failure load, no, beyond this Q sub U here, the load settlement plot will be stiff, no, and practically almost linear, okay. And this type of failure in soil is called the punching shear failure, and this would be now its corresponding load per unit area small q with respect now to the settlement. Okay, so when you are dealing with this loose soil, no, probably you have to consider the punching shear. You have to remember only three things, no, considering the general shear failure when you are dealing with dense sand or the stiff clay. Second, if you are dealing with the local shear failure, so probably your soil is somewhat this, no, this type of soil, no, when you are dealing with local shear failure, the sand or the clay soil. And when you're dealing with the punching shear failure, so you're dealing with this loose soil, no, and you have to remember that one. Okay, so I will show you in this figure for the modes of foundation failure. Okay, so in the x-axis we have now the relative density denoted by this subscript r, and in this vertical axis we have now the ratio of your depth of footing over the width, no, of your footing, df over b asterisk. So as you can see, this is now our foundation, no, having this width b, and this is now the depth of footing, no, from the ground surface to the bottom of your foundation. So if you are going to consider, no, relative density dr of example in this case at approximately 0.4, so by this figure, no, rather by this figure, you can see as you extend a line here, you can see that you can have your ratio of your depth of footing over the b asterisk. Okay, so normally you can get now this relative density result, no, in your soil test report, and then if you have that one, so you can use this x-axis, no, and then you extend a line so that you can determine, no, the ratio of your df over b asterisk. So first you need to consider if you're going to consider, no, this punching shear failure, the local shear failure, or the general shear failure, you know. So as you can as you are going to decide, no, what shear failure are you considering in your design based on our discussion in the previous slide, so you can determine, no, this df over b asterisk. Example, if you have this 0.4 dr, so if you extend a line and you are considering the punching shear failure, so probably at any point here you can get, no, your df. Example, if you use at this point, so you can extend a line until here, so you can get the corresponding df over b prime. So after getting that df over b prime, so you can have now this formula, no, in getting your b asterisk, rather, no, not b prime, this b asterisk. Okay, so by using this one, you have this B asterisk, no? Probably you have to have an initial value of your B and even an initial value of your default footing, no? And then afterwards, you can get now the value of your B prime, in which in this case our B is the width of the foundation and L is the length of the foundation. Okay, so after getting this B prime, so you can get no your estimated depth of footing, no, based on these modes of the foundation failure, considering a punching shear failure. But in case if you consider no the local shear failure in your design, so you must be at this point until this point, no, so you can use somewhat, you can select any point here and then extend to this one, and you can get your corresponding df over b asterisk, and consequently you can have an estimated value of your depth of footing. Okay, so proceeding, we have now those value for square foundation. Your width is just simply equal now to your length, and for the circular foundation, your width is just equal to the length, and this is just equal now to the diameter of the circle. Okay, so we are going now to the Terzaghi's bearing capacity theory in our next slide. Okay, so by definition, according to Terzaghi, we will have now this foundation is considered shallow if its depth, no, df, is less than or equal to its width. Okay, but later, according to some investigators, especially at present, no, the foundation is considered shallow if its depth, no, is equal to 3 to 4 times its width. Okay, but as to Mr. Terzaghi, we have to adapt, no, to this one, in which it is being considered as shallow if it is less than or equal to its width. But it's up also now to the designer, no, to the geotechnical engineer, if you consider, no, shallow with regards now to this Terzaghi's concept, or you can adapt also this one, no, when your depth is equal to 3 to 4 times its width, no, according to some investigators. And you have your own discretion, no, if you are going to use the theory of Mr. Terzaghi, or you can also opt to use this 3 to 4 times its width. Okay, so we have now this following formula, no, for this ultimate bearing capacity. When we are going to consider the square foundation, this one, the Q sub U is just simply equal now to 1.3 C prime in NC plus small q times n sub q plus 0.4 unit weight B times n sub unit weight. No? So C prime is just the cohesion of the soil. The NC, NQ, and N unit weight is just the bearing capacity factors. And this small q is just simply equal to the unit weight times your depth of your footing. Later you will see the formula for this small q. And we have here the unit weight of the soil, and B is the width of the soil. Okay, so this is for the square foundation. Second is we have now for the circular foundation, our Q sub U, they only differ on this third term. We use here 0.4 but 0.3 only for the circular foundation, and the first two terms are just similar. Okay, and for the rectangular foundation, we will have now this formula of our ultimate bearing capacity equal now to this, as shown in this slide. Okay, and with regards also to the factor of safety, by definition, calculating the gross allowable load bearing capacity of the shallow foundation requires the application of a factor of safety, no, and it is denoted by this Fs to the gross ultimate bearing capacity. So by formula, your Q allowable is just equal now to this QU, or the Q ultimate over the factor of safety. Okay, and if you are going to consider the net, not gross, now if you are going to consider the net stress increase in soil denoted by this Q allowable net is just simply equal now to this net ultimate bearing capacity denoted by this Q subnet U over this factor of safety. Okay, you have only to remember, no, if you are going to consider the gross load bearing capacity, so Q all equal now to QU over Fs, no. But if you are going to consider the net, so you just replace this Q all, no, with this Q all net, and this QU is also just QU net. Okay, over the factor of safety Fs. And for the formula of our Q net, no, for this Q net here, it is just simply equal now to QU minus your Q, small q. This is the formula for this small q is simply equal now to the unit weight of the soil times the depth of footing, as you can see in our next slide. Okay, so this is now the net ultimate bearing capacity denoted by this q sub net u, and our small q is just the unit weight of the soil times your depth of footing df. Okay, and we can say that your q all net is just equal now to QU minus small q over the factor of safety. Okay, so this is now the discussions of this Terzaghi bearing capacity theory, and also with this factor of safety, no, in the design of your foundation, considering the allowable Q, considering also the ultimate Q, considering the small q, which is equal now to this unit weight of soil times df, and considering also the factor of safety. Okay, so we will proceed now with our sample problem, no, for this day, and this is now the problem statement. A square foundation is 2 meter by 2 meter in plan, and the soil supporting the foundation has a friction angle of this phi prime equal to 25 degrees and C prime equal now to 20 kilonewton per meter square. And the unit weight of the soil is 16.5 kilonewton per cubic meter. Determine the allowable gross load on the foundation with a factor of safety Fs of 3. Assume that the depth of the foundation df is 1.5 meters and that general shear failure occurs in the soil. Okay, so we can say that the foundation is a square, so we can say that the formula we are going to use this QU equal now to this 1.3 C prime NC plus Q NQ plus 0.4 unit weight B in unit weight. Okay, and this is for the square foundation. So you need also to determine the known parameters. First, we have now this friction angle P prime of 25 degrees. Okay, and we also have now this C prime, no, the cohesion of 20 kilopascal, and we also have now this width of the foundation, which is 2 meters. Next, we have the unit weight of the soil, the factor of safety, and we have now this df, no, the depth of footing, as you can see in this slide, no, equal now to this 16.5 kilonewton per cubic meter. The factor of safety is 3 and the depth of footing is 1.5 meters. So we are going to determine the allowable gross load, no, the allowable gross load. We need to calculate first, no, since our formula is for this square foundation is QU is equal now to this, so we are going to consider this formula, no, and after this we do not know the value of our NC, no. We have this C prime which is 20, but this NC is this bearing capacity factor is still to be determined. So we are going to calculate now the NC. Okay. So by formula, you can use this one, no? This formula of our NC equal now to this cotangent of your friction angle times this NQ minus 1. Okay. But we still do not know the value of our NQ. But as you can see, no, with regards to our references, the book of Braha Imdas and also with Murti, you can use, no, this NQ, this formula of NQ equal now to this E raised now to this exponent, no, of 2 times 0.75 phi minus friction angle over 2 times this tangent phi prime over this 2 cosine squared of this 45 plus phi prime over 2, no? But make sure that your angle is in radians. Okay, you are going to use the angle, no, in radian with this p prime and also with this 45 degrees. This is 45 degrees. You are going to convert this one into radians. So by doing so, we have now this value of our p prime, which is given, and this is 25 degrees. So you need to convert that 25 degrees into radian. So this is now its equivalent value in radian, no? 0.436 over 2, and then tangent of your 25 degrees in radian is 0.436. Okay, and this 45 degrees you are going to convert also this one into radian. So this is the value of 0.785 radian for this 45 degrees, and this p prime equal now to 0.436 radian. Okay, so by that you can use your calculator, no, and you calculate the value of our NQ, which is 12.71. Okay, so you can check, no, this one in the table with regards to the reference books. If you are going to look into the Braha Imdas, you can see that the value there is almost the same, no, 12.71. Okay, so we can say that we can get now the value of our NC based on the estimated and calculated NQ by this formula. So we can substitute now the formula here. Okay, so cotangent, take note again that your P prime must be in radian. So this is now in radian, no? 0.436, and then you can get the value of your NC, which is 25.13. And lastly, we are going to calculate the last bearing capacity factor of this N unit weight, no, subscript unit weight, and we can use now this formula of Hansen, no. Actually, there are a lot of formulas there, no. You can use the formula of maybe Terzaghi and any other authors, no, or scientists. But in this case, I just choose this Hansen, no, formula, because the way I calculated the values, they are almost close, no, to the value indicated, no, in the book by Braha Imdas and also by this B and Morty, no. So you can use any other authors, no, with regards to this bearing capacity factor and sub unit weight. But in this case, I'm just using the Hansen, and we use this 1.5 of your NQ minus 1 times this tangent phi. Okay, so again, your phi prime is in radian. So by substituting the calculated values here, so you can get the value of your bearing capacity factor in unit weight of 8.18. Okay, so from the formula of our QU is just equal now to this 1.3 C prime NC plus Q NQ plus 0.4 unit weight B in subscript unit weight for squared foundation. We can substitute, no, our C prime, our calculated values for NC, NQ, and this in unit weight. This small q is just simply the unit weight of soil times the depth of footing, which are given parameters. So there's no reason that we cannot calculate this one, no, since B also is given. So substituting, our C prime is 20 kilopascal, NC is 25.13, this one, plus this small q is your unit weight of soil, no, 16.5 kilonewton per meter squared, times the depth of footing, df of 1.5, and we have now this NQ of 12.71 here, as you can see it here, no, 12, this is 12.71, plus your 0.4 of your unit weight of soil, which is 16.5 kilonewton per cubic meter, times your width of footing of 2 meters, times the calculated in unit weight of 8.18. So we can get the value of your ultimate Q, which is 1076 kilopascal. Okay. So proceeding, we are now going to deal with this factor of safety, no, since we are going to determine the allowable gross load. So by formula, we have now this Q all, meaning allowable, is equal now to Q sub U over the factor of safety. Okay, the factor of safety is given, no, if S equal to 3, and then our ultimate Q is calculated already, which is 1076 kilopascal. So we can determine the Q allowable. Okay, so we substitute the values here. Our Q allowable is simply equal now to 359 kilopascal. Okay, since we are after with the gross allowable load, so we can use now the formula for this gross allowable load, equal now to Q allowable is equal now to this load Q over the area, no, since this is load per unit area. So since this is a square foundation, so its area is B squared. And then we have calculated this Q allowable, which is 359, and we have this width of the foundation, which is 2 meters. So there's no reason we cannot get the value of our allowable gross load Q. So by substituting these values here, so Q allowable is just Q allowable, small q allowable, no, the value of your allowable gross load, capital Q, is just equal now to the product of small q allowable times this B squared. So substituting here the values, we can have now this 359 kilonewton per square meter times this area of square of 2 meters squared. So this will cancel out, no, the only unit remain is this kilonewton. So this is our value of our allowable gross load, capital Q, equal now to 1436 kilonewtons. And this is probably the answer, no, in this sample problem. Okay, so I hope that you have learned, no, a lot today regarding our foundation engineering subject, specifically discussing the Terzaghi'S bearing capacity theory, and I hope you will also extend, no, some effort from your end, no, not just to be contented of my discussion here in this lecture video, but at some point you need also to solve, no, example problems there in the book of Das or Ibn Morty, using the concepts, no, the formulas and the principles we have discussed in this lecture video of mine. Okay, so I will discuss, no, additional problem in my next lecture video, and I hope you will also consider watching that video, no, to let you understand better, no, the subject foundation engineering. But here I presented the formulas, no, here on how to get the bearing capacity factors of that NQ, NC, and in subscript unit weight. And in some reference books, especially problem solving, no, during our board examination for the civil engineering students, they actually give, no, the value of that NQ, NC, and that N unit weight, no. But if ever you will encounter, no, in the future that the values of these bearing capacity factors are not given. So you are going now to use the formulas here, no, as presented. No, you can actually use here these formulas. No, if ever for NQ, you are going to use this. For NC, you can also use this, and for the N unit weight, you can also use this formula if ever these bearing capacity factors are not given, no, in the problem. Okay, so again, thank you very much for watching this lecture video of mine, and these are now my references, no, before we will end. The Braha Imdas book, The Principles of Foundation Engineering, the 8th edition, and also with the Morty BNS, The Principles and Practices of Soil Mechanics and Foundation Engineering. Okay, so thank you everyone, and thank you for listening and watching, and don't forget, no, to subscribe, no, so that you can be notified and be updated, no, in my next lecture videos. Thank you, and God bless everyone.